The year is Pripyat. It's Ukraine 1986. Early in the year, it's April. Something bad has just happened. I don't know if you guys have heard. There was a big boom over there. And I'm not talking young Sheldon. Shut a young Sheldon, put him in the corner. This wasn't a small oopsie at all. This was a big one. According to the International Nuclear Event Scale, this is a 7, which is the highest they go. Only happened one other time. I don't know how you have a small oopsie. I don't know how you have like a number 1 or a 2 on this. Feels like a nuclear reactor has kind of always got to go bad. We have $700 billion in damages. The biggest mistake monetarily ever, I believe. And over 500,000 people are here to try to clean up this mess. The big question is, what actually happened at Chernobyl? Most people just know that something blew up, something went wrong. But I want to break down into what really happened. Now, one of the big questions is, how did we even get here? How does something like this happen? At the start of the day, they were doing a blackout conditions test to try to find out how the reactor would respond in very low power situations. They have backup generators, but that's not going to run the plant forever, so they got to find something to last the time in between. And from all accounts, they noticed something bad was happening and tried to shut it down, and afterwards, it blew up. After the actual explosion, there was a big exclusion zone where everyone had to leave. It started at 10 kilometers. Editor put up the conversion rate for our Americans. That was increased to 30 kilometers later on. It took a very long time for the Soviet government to actually admit anything was happening. They didn't say anything until 2 days later when radiation was detected all the way in Sweden. Editor put a map on how many kilometers Sweden is away from Russia. But what's the damage here, alright? Some money? A big boom? No, 16,000 deaths have been attributed. Some say even more because of the long-term cancer fallout. Hundreds died very quickly due to the acute radiation, and thousands died to the thyroid and other forms of cancer they got afterwards. But those are just stats. Let's break down what actually happened. I've got my handy whiteboard here, aka MS Paint. First off the question, how does a nuclear reactor actually work? How does this whole thing work? How does something like this blow up? It's actually not that hard. You have a fuel source, in this case represented by green. Green is radioactive, as we all know. A common fuel source is plutonium or uranium. These rocks are very angry. They go through a process called radioactive decay to come to a more stable isotope. Types of particles they can shoot off are alpha particles and beta particles. Beta particles are basically an electron. They'll just shoot those off to make a neutron into a proton. Alpha particles are the nucleus of a helium-4 isotope, which is basically 2 protons and 2 neutrons. So it's helium without any of the electrons to balance it out. During the process of them shooting off these particles, known as fission, that means to pull 2 things apart, and that's what they do. It will shoot off these particles as well as generate a lot of heat. All that energy has to go in some form, and heat is one of the biggest byproducts of these kind of reactions. Heat will be represented by this red, orange, and yellow glow. Do not mistake it for fire. It does not generate fire. Now, these radioactive elements are in a very dangerous state. They are very close to freaking out and shooting off a bunch of particles, and they slowly decay over time. As the radioactive fuel decays, some of it will turn into not the fuel. It'll decay into other metals, as well as generate that heat. That heat is used to heat up water. That water will then turn into steam, and that steam can push a turbine. Now, if this sounds familiar, this is because this is a steam engine, like trains from the Industrial Revolution. They were basically the same thing. Apparently, we haven't cooked up a new one. I'm sure there's new ones, but nuclear reactors are steam engines. There's no scary green goop. The fuel won't just decay into other metals immediately. It has to go down in a ladder of sorts to try to get to the most stable one. Most elements beyond lead are very unstable, and they're all radioactive. The whole time you're kind of trying to mediate how explosively your fuel is decaying and shooting off these neutrons. Moderator rods and control rods all mediate the flow of neutrons throughout the reactor. If a neutron hits your dangerous spicy elements like uranium, they'll react even more since the sudden energy is going to make them want to release it some way. If the neutron hits your lame elements like boron, it's not a big deal. And these neutrons are very small. We are basically shooting bullets into space, hoping it hits a bullseye. If the neutrons do manage to hit another fuel, that fuel will then spring off other stuff, which can go hit more fuel. If this reaction keeps happening, that is when the reactor has gone supercritical, which means basically you can't stop it. Unlike other chemical reactions that you're able to kind of mediate the flow and the speed based on all sorts of stuff like pressure, temperature, catalysts, adding other things to the reaction, nuclear reactions will just kind of always go. You can't do anything about it. It's a natural process. In this kind of reactor, one of the main buildup is xenon. It can get burned away, which basically just means it'll turn into another element that isn't going to get in the way as much. The specific xenon isotope that is present is very good at taking all of the neutrons. It has a very big area for it. Now, this whole process is going on for the rest of the reactor, but it wasn't a normal time going on. Since they're doing blackout conditions, they have to decrease the power that they're outputting from about 3,000 megawatts of thermal energy to 500. Editor put up if 500 is a bigger number than 3,000. The answer is, I'll spoil, no. Even after they do everything, they can't quite get down to 500. The lowest they get is 700. And even after everything basically shuts down, they get down to 30. As the power keeps falling below what they need for the test, they try to increase the reactivity by taking out the control rods that are blocking these neutrons from hitting the other stuff. After taking out the control rods, they're able to get up to 200 megawatts, which is still too low for the test, but not basically shut down like 30. And they try a bunch of stuff to try to increase the reactivity. One of them is turning up the coolant pumps to increase how much coolant or water is getting strewn about. The idea is as water heats up to turn to steam, you pump in new water that is colder, and that way you don't allow things to just blow up and get really hot. They will not stop releasing heat energy and getting hotter. In the actual reactor, I believe reactor number 4, there's a big circle. Now I just finished drawing the rest of the diagram off camera, but that's basically roughly what it looks like in the reactor. And as the test goes on, they have pulled out almost all of these control rods. In this specific reactor, there is a flaw. It has a positive void coefficient, and if you don't care what that means and it's just jarples, basically instead of when water heats up to become steam, the steam decreases reactivity, those air bubbles called voids are actually increasing reactivity and making things speed up. All this stuff is going on. They're at the point where all the control rods are basically taken out. They've got a bunch of steam. They've got a bunch of xenon that they can't actually burn off. The xenon is taking all the neutrons from all of the fuel. So almost nothing is going on. It is in a very dangerous state. Now, as they're finishing up the experiment to test the blackout conditions, there's a big button called the AZ5 button that'll initiate a scram. The scram just means emergency shutdown. To do that, all of the control rods, including the ones that are normally partially out and the ones you have manually taken out, will all very quickly go back in. The hope is that if all the control rods are in, the uranium can't interact with each other. Unfortunately, there was a flaw with these that was known at the time. The tips of the control rods have small graphite on them. The idea is to move stuff out of the way, and for a brief moment, it increases reactivity instead of decreasing it. These rods take about 20 seconds or so to fully insert in and out, so for a bit the reaction is going much faster than it should be. During this, heat very quickly climbs, instantly flashes all the water, turning it to steam, and all that heat and pressure is too much for the reactor, and it blows up. There was a second explosion shortly after, but that was probably just a griefer or something. That wasn't the reactor's fault. The last really interesting thing that happened, immediately after the explosion, it launched all the graphite tips everywhere that firefighters saw and tried to pick up. That graphite is very heavily irradiated, as well as a bright blue glow emitted from the top of the reactor, since the air itself was literally being ionized. I believe we didn't get too many pictures of this, so editor, if you can put up a picture of what this might have looked like. Most interestingly, I was not able to find anything about the Wither being killed on this world. No one had the achievement, and we are yet to find the Wither's skulls. So how they got a beacon, I'm not sure. Probably admin abuse on the Soviet Union's part. Whatever. Moral of the story, editor, if you could put up a picture of morals, that'd be great. Leave a dislike and hate comment if you don't like this video. Hashtag Chernobyl.